One of the most important proofs in Euclid's The Elements is his famed parallel postulate, which can be found in Book 1. This postulate claims that given any straight line, you can name this line L, and any point not contained on that line, point P, there exists one unique line through point P that is parallel to line L. So he begins this proof by assuming that there is at least one line through P that is parallel to line L, and he is able to construct this line by proposition 131, which he has already proved, that states that you are able to draw a straight line through any point that is parallel to a given straight line. So he's able to construct line M that is parallel to line L. Next, by proposition 112, he is allowed to construct a line through the given point that is perpendicular to both lines. So he constructs F as a transversal that is parallel to both lines, and it makes these right angles with the two lines. Euclid then assumes that there is a second line through the given point that is not the same as the first line, such that it makes an angle alpha with line F. So he assumes that there is a line, and we call it N, that makes this angle alpha with the line F, and we know that alpha is not equal to 90 degrees. So from proposition 129, we know that if a straight line passes through two parallel lines, the sum of these two interior angles has to equal 180 degrees. Well, since we know that alpha is not equal to 90, but we do know that the second interior angle does equal 90, the sum of these two angles cannot equal 180 degrees, therefore line N cannot also be parallel to line L, meaning that line M is the one unique line that is parallel to line L through point P. So this parallel postulate was very important later on in the proof or the origination of log spherical geometry. So we return to it a couple centuries later in the 19th century. Johann Lambert, a Swiss mathematician, physicist, philosopher, and astronomer, tries to prove this postulate by first assuming that it's false and then trying to prove a contradiction. So how he goes about this proof is he imagines an arbitrary quadrilateral that he knows has 3 right angles, and he makes 3 hypotheses about the 4th angle. So his first hypothesis is that it is right, his second is that it's obtuse, and his third is that it's acute. So he's able to prove the first two by saying he knows it's right because of Euclidean geometry. There has to be 360 degrees in this quadrilateral. He's then able to actually prove that it could be obtuse by first imagining a spherical triangle in which the 3 angles add up to being larger than 180 degrees. But he has trouble proving that it's acute because that would need him to imagine this quadrilateral on a sphere with an imaginary radius. But however, Franz Taurinus, who was inspired by this work of Lambert, developed this notion of the spherical triangle and was able to actually form an equation relating the sides and angles of this arbitrary triangle. So he considers a triangle that's on a sphere of radius k, and this spherical triangle has angles A, B, C, and sides A, B, and C. So he's able to come up with an equation that relates these sides and angles. So this equation is cosine A over k equals cosine B over k cosine C over k plus sine B over k sine C over k times cosine of big A. And he's able to transform this into a log spherical equation by assuming that this triangle could also be on a sphere of radius ik, and he replaces this equation with a radius of ik instead of k, so it becomes cos A over k equals cos B over k cos C over k plus sine B over k sine C over k cosine A. And this is the equation that has defined what we know as log spherical geometry, which has recognized that this kind of geometry was no longer possible in the Euclidean plane, and shows how geometry has transformed over the years, transformed over the centuries from being something more concrete and something a little bit more abstract.